Now listen. Okay, just a few things. So everybody have your slides available. We're gonna do this for 20 minutes. We'll see how far we can go. Okay, and then once you guys cannot tahan anymore, then we will take a break. Is it okay? So please pay fullest attention for the next 20 minutes. Hey, thanks. Okay, now listen. So the first thing that I want to highlight. Okay, the first thing I want to highlight is if you take a look at your slides, right? Everybody have slides. Now, remember we started on this topic on drawing of symbols. You remember?
Yes.
Drawing of symbols, forgot already. It's okay, we'll try again. Now, if you take a look at the first objective, do you all see the first objective? First objective on your slide. It says draw, interpret circuit diagrams and set circuits containing electrical sources, switches, lamps, resistors, ammeters, voltmeters. Now, what I want you to do is quickly try to remember what they are and draw it in on your notes. That means above the electrical sources, drawing what you remember of a cell, a battery. Above the switch, what it looks like, draw the switch. Draw the lamp, draw the resistor, the fixed one versus the variable one. Draw an ammeter and draw a voltmeter right now. Everybody, try. On the slide. Draw on the slide. You can draw on the slide, no problem. But label them. Electrical source, resistor, lamp, switch. Try in. What are you supposed to do now? But you're not sleeping, so work lah. Might as well. Hey, hello. What are you guys looking at? Admire who?
Very nice.
Why? Admire Mr. Nathan's school you are?
Yeah, no lah. Admire his shirt, his school really hard.
Hurry up lah, do your work lah. You want me to hug him?
Yeah, no. You can
Good.
I don't like to. I don't touch my students. It's okay, I'm not Mr. Nathan. I don't want to. Okay, Benjamin. Strike one. And this is on record. Very good. I'll remember for life. I'll put it on YouTube.
And the whole world knows.
Yeah. Strike one, Benjamin. Are you done? Everybody have it? Okay. Okay, Benjamin, come. Go and draw on the board since you're so active. Yeah. I know you can. You can draw. Draw all the different components on the board, then you can name them. So Benjamin, you put it on the board. Okay. You draw all the things. Remember the positive, negative signs. Huh? Yeah. Correct. Okay, I'm gonna. Sorry. Not on Monday, but I drew on the board. So these are the notes that you guys can keep. Yeah.
Ammeter.
Okay, he's doing well so far.
AMMETER. AMMETER.
Then still got this one. That is the
Resistor.
Okay, once you're done and you're looking at Benjamin's drawing, sketching, I want you to look at the next learning outcome. It says explain what is meant by current, potential, difference, and resistance, and their units. This one I also explained a little bit. Can you guys also write that into your notes? Current, potential difference, resistance, and state their units. I talked about that before.
The
Yeah.
fixed and variable, that one is called what?
Resistor.
What do you mean?
Benjamin done? Thank you. Nice talk. Okay, remember to write resistor. And then remember to write switch. Did you miss out anything?
Wait, what's the FI? The one is the resistor, then fixed. Fixed. I thought you said the
Fix. Yeah. He wrote a fix. Fixed variable. So this is a cell, correct? And a battery?
It's 2 or more.
Yes, like that. 2 or more.
Total battery can have 2 also.
Can, but I like to draw 3. One is called a cell. Yeah. Okay, everybody have those? Very good. Now, once you're done with this, okay, we go to the next point, which is explain what is meant by current, potential difference, and resistance. So current, I talked about this yesterday. Potential difference,
So you don't think potential difference?
I did. I did. I did. The only thing I didn't teach was I didn't talk about resistance. I didn't. Not officially.
You say what? Make the light dimmer.
So, I did talk a bit about that, okay? I did talk a bit about that. Okay, so, do you remember what is resistance? Sorry, we do current first. What is current? What did I say? Good, amount of electricity or amount of electrons. So, this has to do with amount of electrons. Hang on, Benjamin. What is the unit?
E.
Yes, ampere. Ampere, and the short form, the symbol is A. Very good. What about potential difference?
The speed.
The speed or energy. Amount of energy. Amount of energy, right? Of electrons. Yes. Yes, correct. And the unit is volts, and the symbol is V. How about resistance?
Decrease the amount of
Yeah, control the flow is one thing.
The light, make it dimmer.
Yes, I talked about that. I said putting a resistor would reduce the brightness of the light. So think of resistance as resisting the current. Resisting current. Okay, make it don't flow so much. Resisting the current. And resistance, the unit is called ohm. Ohm. Yes. And the symbol is like this. Yeah.
看过
看过 right?
It's the omega sign.
Yes, it's the omega sign. Actually, in American English, it's called omega. You know James Bond movies? James Bond movies. I love James Bond movies. So James Bond always wear the omega watch. Last time when Pierce Brosnan was the James Bond character, he always wear the omega watch. In American, huh? Who wear Razor $80? This is not Razor $80. Yeah. Okay, questions. Ned, are you writing it down? This is important. Please try.
Right. The front
Lemon,
line.
got it?
The front line for the sign, is it sideways?
The front line. Actually, the omega, the symbol, right? As long as you draw like that, can already. It's okay.
One high, one low, one.
No lah. I draw very badly lah. Sorry lah, Ray. One high, one low. Okay, as long as it's the same, it's like like that lah, bump like that can already. 这样可以了。Okay.
So I cannot see.
Oh.
That give me a shade.
Come closer lah.
Omega.
That's not very nice. Okay, questions. Okay, so far, can hor? Okay, don't worry, we'll revisit this again. I just want to go through some of this because I talked about this yesterday. No, the day before. So I want to recap and help you put it on your notes. Questions. Okay, now. Okay, all okay? Now, we're going to take a look at series versus parallel arrangements. Okay, that's the next slide. And then we go right. It talks about the next point. So the next slide is investigate effects of varying resistance on the current in the circuit using fixed and variable resistors. We'll talk a little bit more about this. Okay. And then the next slide says explain qualitatively the chemical, heating, and magnetic effects of electric current and list some applications. So basically uses of electricity, what we can do with electricity. Have you guys heard of electromagnets before?
Yeah.
Yes, right? Have you guys, actually frankly speaking, almost everything around us is run by electricity, right? Even our phones, our watches, the fans, everything. So electricity can do a lot of things. So these are just some ways of looking at it, the effects of electricity, okay? The next slide says, explain what is meant by power and state is SI unit. Okay, we'll talk about power a little bit. And then the last bit is solve simple problems on cost of using electrical appliance, things like how much it costs and things like that. I don't know whether you guys, I know you guys don't pay your power bills at home, but I do, so I know how important it is to save electricity. Yeah? Okay. Yeah, something like that. Okay, next one. Some electrical systems, some hazards. Okay, electricity is very useful but can be very dangerous. So what are some things you need to do to prevent? I'm on the third slide already. I think the slides are arranged. Left corner one, left top corner one, then
Right. Top right corner.
2 is the right top corner, and then 3 is the bottom left, and then 4 is the bottom right. So top left, top right, bottom left, bottom right. That's the sequence. It's zigzag one. Okay? So remember, top left, top right, bottom left, bottom right. So zigzag. Okay? Like that. I write for you. 1, 2, 3, 4. Okay? I know. But sometimes it's still good to emphasize. Some people, but you not very good, Okay. Again. So I'm on slide 3 now. Slide 3. Okay? So electrical hazards, important. Precautionary measures, important because I want, at least at the end of the lesson, I hope the least you guys will know is how dangerous electricity is and how to be careful when you're using electrical appliance. I don't want you guys to kena zap and then died, then very sad. Because I still like you all,
Thank you.
Okay, discuss the importance of for Singapore, which has no natural resource. So we talk about conservation, electricity, also very important. And then demonstrate precision and accuracy in making instruments. So I already asked Mr. Chua to design some lab experiments for us. So we can go to the lab, have some fun, learn a little bit more about electricity. Okay? Can Alright, okay. Any questions so far? Can I go some more minutes? 5 more minutes? Will you take a break after that? I don't know. Is it okay or? Okay we try. Okay, now take a look at slide 4. Now that is a simple electrical system, right? Now what does it consist of in the system?
Switch, wire,
The bulb,
cell.
the switch,
A cell.
and a cell.
Electric
Now,
cell.
if you turn, let me see. Okay, so that's a very simple system whereby there's a switch, there's a cell, there's a light bulb. Now, of course, ladies and gentlemen, modern circuits, like for example your phone, they don't look like this. Like for example, your phone, your whatever iPhone or Samsung, or you know Samsung, right? The switch, right? There's a switch. Switch here. This switch. Switch here. The switch don't look like that, don't have the flip one, Even the switch here, right? It doesn't look like that, The switch here. Right? So these are very old switches, but the idea is the same. The reason why they look like that is so that you can see the insights, the working of it, okay? Now, if you turn the next page, slide 5. Now, very simple concept. If the switch is closed, right, means that the circuit, a complete circuit is formed. So I got fill in the blanks, Okay, so for example, it says here, when electricity flows from one end, blah blah blah, wires and the light bulb to the other end of the electric circuit cell,
Complete or
closed or complete circuit is formed. A closed or complete. I like closed better, so write the word closed. Right, circuit is formed. Because the circuit is closed, the light bulb lights up right? Very easy, right? Common sense. Can, but I short leash, I rather stand here, I don't want to stand there. I want to talk through this. But y'all can see, right? Y'all can hear, right? So y'all fill in the blank already? Alright. So, very simple. Then of course, if you turn to go to next slide, which is slide 5, right? 6, 4, 5, 6, 6. If you turn to look at 6, concept of open circuit also very simple. If the switch is open, then the bulb does not light up. Correct? Open circuit, right? There's a gap in the circuit, right? When there's a gap in the circuit, electricity cannot flow, therefore it's called open, and therefore it's incomplete, it doesn't light up. Now, here is something very important you all must understand.
Okay.
When the circuit is open and there's a gap, what is in the gap? Air, right? Now, yes. No, don't worry about water. Now, listen to this, very important. No matter what is the gap, and whether it's air or water or anything, if the voltage and current is high enough, it will still pass through. For example, lightning. How lightning happens is that the cloud, the water vapor in the air, in the clouds, right? They move across one another. Static electricity is generated, right? Friction makes static electricity. So there's a potential difference between the cloud and the ground. That's how lightning strikes. When the difference is large enough, the electrons in the cloud will jump or move from the cloud to the ground, or from the cloud to the highest point. It could be a tree, it could be a building, or lamppost, or anything.
The fastest way to reach the ground.
Hang on. So when that happens, electricity is produced, because electricity is about moving electrons. So my point to you is this: no matter what you think the insulator is, even if let's say rubber glove or whatever, if the voltage and current is high enough, it will still pass through whenever there's a potential difference. That means if the air has a lot of electrons, the ground don't have, there's a difference, it will move. Okay? Question? Yeah. So same thing. So let's say, for example, I don't know about you, but I always have a tendency to get electric shock in the shopping center, my favorite NTUC. And I can tell you the worst place to get it, or where you always get it, is actually the
Trolley.
no, escalator. Yes, those of you who experience it a lot will know. Now, why escalator? Because the escalator has a lot of moving parts. And if you take a look at the escalator carefully, right, there's a brush that somehow trap like rubbish or dirt to prevent it from going into the escalator inside. That is the brush that generates static.
I thought it's wash only.
Okay, now listen. Don't put your leg in the brush. Don't. Because if
Jangan
you
caught
go,
die.
yes, your shoe might be caught inside. It's okay. If you want, if you like to have your feet trapped there, then solve your feet, no problem. Go ahead, okay? Just don't come crying to me and say, Mr. Chan, my leg gone. I say, Obi, I'll say, ha. Okay, now. So, but coming back to the topic about static electricity, the reason why escalators generate a lot of static electricity is because the moving parts brush against, the brushes at the side, and it will collect electrons. So sometimes, if you unknowingly you hold the handlebar, or you hold sometimes you get transfer. The worst places to get are actually the metal railings near the escalator, not even the escalator itself. The metal railings. Sometimes you touch, especially I know NTUC will have, you touch it. Sometimes you get shocked, sometimes you don't. It depends. Right? Depends. Yeah?
I'm not gonna.
In exam, right, they ask, there's a gap between the wire. Then the song you say, if the voltage is high enough.
Yes.
What we write?
No, okay, now listen, very simple one. In the exam, in the test. Now, what I'm saying is the truth, right? It depends on the voltage and the current. Now, of course, when you take a look at the exam question, you must understand what is the source, electrical source. If the electrical source is a battery, like that, of course it won't happen now. Right? Because battery only how many volts only? But, okay, frankly speaking, hang on, Clement. Now, even if, let's say, it is our domestic electricity, domestic. Do you know what is the voltage for domestic? Do you know? 220 to 240 volts. 200 volts.
Let's die.
So, That is why in the past you cannot charge your phones using this because the voltage here is very high. Your phone will 爆炸, right? But there is a way to change the electric current. There is a way to change the electricity. Have a way. And that's why you have these small chargers where you plug in your USB cable, correct?
All the resistors.
Yeah, right? So inside there's a circuit board that allows you to convert some of the energy to something else. No, not just, it cannot be just a resistor. There's something else. Actually, that something else if you're interested is called a transformer. Not the robot, not the robot, not the robot. Transformer. Serious. I'm not joking. You can buy a transformer.
Is it a microwave? It's a microwave.
And it's not the robot. Okay, now what a transformer does actually, a transformer is able to change the output voltage. Let's say the domestic voltage 240. You can use a transformer to change it to 2 volts or 3 volts or 4 volts. Don't worry, I don't think this in the syllabus. If you're interested, we can talk about it if we have time. But this is a very interesting topic to transform the electricity. But we'll talk about it another time. Okay. Wait. Okay, Ken? Okay, Katana? Charger.
Compared to the normal one, right? So what if?
No, different current. Not voltage, it's current.
So then if I charge my phone using the iPad one, what will happen now?
Have you tried before?
Yeah.
What happened?
Charge
Exactly, very good. So here is the idea, right? Those of you who are rich enough to have an iPhone and an iPad, you realize that the iPad has a larger capacity than an iPhone, like larger, more battery because bigger, And you realize that if you are unfortunate to sometimes forget you charge the iPad using the iPhone charger, it's very long. Because the iPhone charger has lower current. That means current is what? Remember current is amount of electrons, right? So imagine if you deliver less electrons, then it takes longer time to charge, correct or not? But if you use the iPad charger on the iPhone, it charges quite fast because the iPad charger has more
But battery
current.
run out damn fast my phone like dying.
Difference, so maybe the battery got something wrong. It's okay. Now, if you are interested, we'll talk about batteries later because there's a topic, there's a learning outcome called chemical effects of electricity. So we'll talk about that. Okay? Good. I guess I'm interested. Very good. Okay, now, next slide. Lemon. Simi is static. You do something then you don't do good.
Wear something on
Eat concrete.
There's actually
Okay, now listen. Now in Singapore, right? In Singapore, because the weather is very humid, a lot of water. No, it's very difficult. And usually it's in aircon areas that the air is drier, then you get static more. Wait. Sorry. Now, is there a way to prevent it? I will let you guys to think about this because this is a very good question. It's a very good problem, right? But I want you to think about it when we learn more about electricity and how it works. I hope you guys will get some answers. I'm not going to answer you first, but I want you guys to think about it. I think it's a very good question. Thank you, Clement, for raising that. Okay, can I go to the next slide, which is slide 7, right? The bottom left corner, second page. Now, how do we represent circuits? It's important that you learn how to draw. Drawing is important. So if you take a look, that is how you draw. Now, the first answer is an electric circuit can be drawn as a circuit diagram. I write for you. Circuit diagram. Circuit diagram. Okay, Ken? Then after that it says, instead of actual components, the circuit diagram use circuit symbols. Okay, so this is all we have been doing on Monday, circuit symbols. Okay, Ken? Okay, check already. Huh? Still okay ah? I think I lost about. Hey, come on, still okay then. Oh, I need still awake.
Wow, that's a
Wow, I need still
Oh shit.
Good job, Annie. Awesome. Everything is awesome. Okay, next. Ace. Alamak, I recorded that. Okay, I will delete it. No lah, just kidding.
Okay.
Oh no. Okay, sorry. I added a blank slide. Okay, let's finish up with slide 8. Slide 8, last slide. Now, here my. Yes, Steven. What do you want? Oh, okay. He's clapping. Okay, now here might be some clapping. Why you laugh? Okay, so slide 8. So conductors and insulators. Here there may be some clues on about how to prevent getting electric shocks. Now, a material which allows electricity to pass through it is called an electrical conductor, right? Examples like metals, copper, iron, all metals are good conductors. Now, why? You don't know why? Why are metals good conductors?
The atoms.
Because they're strong. No lah.
What it's made of, right?
Very good. I know Benjamin guessed one, but it's a good guess. Well done. Okay, sorry. Huh?
Also me.
Ernest
Also me.
Okay, now you are right. Okay, you're right. Hang on. The reason why metals. Anyway, got metal ruler. Let me go. Now the reason why. Thank you. Now the reason why metals are good conductors. Never mind. I used to have I tell you this story. I used to have a geography teacher when I was in secondary school who hates the sound of dropping metal rulers. One day we decided to play a prank on her. We all coordinated. The whole class dropped at one time while she went crazy. Screamed enough for half an hour.
I tried not.
Very funny. Sorry I was in a boys' school we were very cheeky. No, only at Pro 2.
Wow.
I'm recording it, I know. So if you have played a prank on me, I will confiscate all your metal ruler. Alright, now.
Secondary ruler.
Strike 2, Benjamin. Hey, where are notes? On your left. Okay. Now the reason why metals are good conductors, as Benjamin has mentioned, is because metals, interestingly, they have a lot of electrons. You're right. Floating around.
Then the potential difference, right?
No, not potential difference. Now, you must understand a little bit of how it works. So I'm going to take the next 5 minutes just to, wait, I finished the blanks first, Ken? Then I'll describe how it works, okay? I finished already. Okay, the next line, right? A material which does not allow or prevents electricity from passing is called electrical insulator. Okay, very easy. I want to finish this content first, then I'll share a little bit. Why your ruler sticky one?
Oh.
Are you sure it's glue?
I'll try my hand.
Now it becomes slippery one.
Recording
Yeah.
Music lesson.
Okay. Alright. You guys ready? Alright. Okay, last thing before we go. Okay, now, basically, how does electricity flow in a wire? Okay, the idea is this. Okay, so imagine if, let's say, this is a metal wire, of course, enlarged, very big. You can imagine that there are a lot of electrons inside. Okay, a lot of electrons in this. Now, what happens is this. If let's say I connect a battery to it, right? And the battery provides the energy to move the electrons. So you can imagine the way how it works is, if the battery provides the energy to move the electron starts to move. So it moves from this direction, let's say back to this, and if I connect a light bulb to it, and if I force electrons to move through the wire of the light bulb, and that causes it to become hot, and then give out light, you'll glow, right? You'll light up. and then you continue in this way, the movement. So the reason why metals are very good conductors is because metal itself has a lot of electrons floating around. It's very easy for a battery to connect to the metal to push the electrons because the electrons are already moving all over the place. It just needs some, in a sense, like encouragement to move in one direction. Hey, one direction. Okay, never mind. Yes, correct. It provides the energy to move. Both. Have both and current. Because it will allow a certain amount to move. Yeah, you're right. If there are no electrons going, means it's an insulator. For example, plastics, the way the material is inside for plastics is that all the electrons and atoms are all so-called like locked. So cannot move. So because it cannot move, even if you connect a battery to the plastic, there are no electrons to move. So therefore, these things are insulators. Wait, I know Clement has a question. Yes, Clement?
Take battery, take
I don't get. Okay, never mind. Okay. Yeah. Some other. Yeah. Then. Can you stop playing the board? Before I put you on one and push you down the stairs. Then.
You can make the plastic is high if there's enough weight to move the electrons.
Good point. So the question is it possible to convert this into a conductor? Of course, my point is, yes, it can be, provided the current and the electricity is strong enough. However, I'm going to tell you this very interesting concept.
Your milk, right?
You melt, yes, because of the amount of electrons passing through. Now, there's one very interesting idea that allows a metal to work as an insulator. Very interesting concept. And this is called the Faraday's cage. Not Ferrero Rocher lah. Faraday's cage. Anybody heard this before?
It's to block radio waves.
Very good. Now, the Faraday's cage is a very interesting structure. Now, anything can be a Faraday's cage. A very simple example is a car. You remember Major Chong showing you the video of the storm, the thunder, lightning, whatever video? Okay, I will try to find it and I'll share with you on the LMS. Now, actually, there are some. So wait. Slowly. Now, the reason why that a car is an insulator, it means let's say there's lightning, thunder and lightning. Actually, a very safe place because being in a building is very safe because buildings have your lightning, the Chinese call it 避雷针, the lightning rod, right? Lightning rod. But the other place that's very safe is actually in your car or in a plane, even in a plane or in a car.
Wow.
Hang on. So when you're in a car and if lightning strikes, right? Somehow the car would deflect the electricity coming. No.
Why if it's already black?
Yeah, because it's black already. Alright. Okay, now listen. Okay, I'm gonna stop my recording. Stop. Alright. Shall we take a look at slide number 10? Those of you who don't have, because Joel forgot to bring, it's okay. You can share a little bit. Please don't blame him. I think he's doing as best a job as he can. So, we all slip once in a while. So, please forgive him. Are we ready? Slide number 10. The one that says, what is an electric current? 9. Okay, then sorry. Slide number 9. What is an electric current? Okay, now, I remembered I did talk about electric current, and I said that electric current is measured in what units? Ampere, right? Ampere. Okay, I'm going to write on the board. So current is measured by something called ampere, and what is the SI unit?
A.
Very good. A, right? Okay. Nat, where's your stuff? Yeah. Okay. So here are some of the things that if you take a look at the slides, right? Number 9. It says an atom is made of a nucleus with electrons moving around the nucleus. Do you guys remember? Have you ever seen this before? Wait, I draw for you.
Yes.
Yes.
Do you remember this symbol? Jimmy Neutron. Not Jimmy Neutron? Jimmy Neutron, right? Now what does this symbol represent? Okay, so in the past, right? In the past, this symbol has always represented the atom, right? And we know that what's in the center? We call it the nucleus, right? But what are these rings? So these rings actually represent electrons that are moving around the nucleus. Now, to be honest, this model, you can draw. But I want to tell you that this is called a model. Now, why is it called a model? Because nobody has ever seen this before with their eyes. Because the atoms are very, very small, correct? Nobody has seen this before. So this is a model. Model means this is what some scientists believe atoms look like. So it's called a model. Now, in reality, as more information and as advances in technology, scientists are starting to realize that an atom may not look like this. May not. Okay, but it's okay. At your level, at our level, looking at science and everything, we can still assume that it looks something like this. There is a nucleus in the middle, and there are electrons floating around. Okay, so I put here electrons. Now, when it comes to electricity, right, what we're interested in is the electrons. So you can take a look at the second point, right, on the slide number 9. It says, circuit wires are made of metal, and to get an electric current, electrons in the metal atoms move from one atom to the next in the wires. So if you take a look at the diagram, do you see the diagram in the slide? Okay, the bigger balls, they represent atoms. The smaller balls, they represent electrons. Okay, so that's the idea. So you can think about the wire as the cylinder is an enlarged, and you have atoms inside and then electrons inside, but the electrons like floating around. Do you notice? Okay. So the idea is this: for electric current to take place, that means for energy to take place or electricity to move, actually it moves by the electrons. Electrons move from one atom to another atom to another atom, so on and so forth. Can you imagine that? Okay, it's okay. Huh? Oh, not answering me. Okay. Okay. Can you all see that in the slides? Do you all write in the words already? So the first point is an atom is made of a nucleus with electrons moving around the nucleus. Then after the second line is circuit wires are made of metal. To get an electric current, electrons in the metal atoms move. Move. It's there. I'm just reading. The second blank at the second sentence is move. The first blank is electrons. Then after that is around. And then the second sentence, the blank is move. But you can draw in this model. It's okay. Questions? Alright. Yeah, I'm recording. Okay. Now, so therefore, if you turn slide number 10, what is an electric current? Basically, the flow of electrons in one direction. Remember what I talked about yesterday, right? One direction is called an electric current. Okay, so electrons moving in one direction. So I'm going to put again, electrons moving in one direction is called an electric current. Okay, this is the importance. Okay, if I ask you, if the question asks, what is an electric current? If the question is asked, what is an electric current? This is it. So the question is, what is an electric current? The answer will be electrons moving in one direction is called electric current. Or electric current is electrons moving in one direction. Questions? Okay, Ken? Okay, not too difficult. Okay, next slide. So the idea is this, right? Remember the battery? Remember the battery? And remember that there is positive and negative, right? So question, in what direction will the current move?
Positive to negative.
And that is wrong.
Electron field.
Okay? So, but actually, when you say from positive to negative, you are still not wrong because it depends on what current we're talking about. Now, here's the confusing part. Correct. So, if we are asking, what is the is it electron current?
Electron flow or positive.
Yes. So if it is electron flow, it will be from negative to positive. Electron flow from negative to positive. Because electrons are negative, right? So negative repel negative, but they are attracted to the positive, yes? So it will flow like that. Correct? Okay, so I draw here, electron flow will be like that. Like that. This is called what?
Circle.
Circle with arrows.
This is called what? Clockwise.
Never say from clockwise or
Oh,
anti-clockwise.
sorry lah. Now I tell you lor. This is called clockwise lah. It's okay. I never scold you. Okay lah, you do 1 mark lah. Happy now? Now, so, then what about the other current? It's called conventional current. Conventional current flows from?
Positive to right.
Yes, positive to negative. And it flows like what? Like this.
What is conventional?
Conventional means traditional,
Issue one.
normal, or traditional lah.
Then every time you see like that, what is
Just wait. You don't erase.
Okay, so conventional current will be, in this example, anti-clockwise.
But what difference?
Okay, somebody asked, so what's the difference? What's the big deal? Yeah, it's correct. That's a good question actually. Because whether the current flow this way or conventional current flow the other way, it doesn't really matter because if you put a bulb here, no matter which way it flows, you think it flows, it's still like that.
But you will take more time on both.
Not much difference lah. Not much difference. But you're right. I
Then why
think.
did they even make this?
Now, why they make this is because the reason why conventional current is from plus to minus is because before people understand that electricity is from the electrons, right? They believe that it's from plus to minus. It's just a way of thinking. Only later part when they discovered that electricity is actually about electrons, then they believe that it's from negative to positive. But either way, they believe the 5 bar will still light up lah.
Now you still believe
Now they still believe. Okay, never mind. It's okay one. Next slide. Okay, which is what I talked about.
So do you exam which side of
During exam, which side also can, unless the exam question asks very specifically
Electron flow.
electron flow or conventional current. So you can start complaining, say, wow, like that you give me more things to remember. But so sorry. It's like that. Question. Hey.
Sorry, you do.
Hey, throw things.
No, I wasn't throwing. Flying, the thing flying. Teleport. Do invention.
Okay. Okay, is it okay? So that's slide 12. Any questions? Slide 12? Are there blanks to fill in? Have Okay, slide 12. It says that in the early 1800s, scientists know about electrons and thought of current as something moving from the positive to the negative.
Before that one is what?
Huh? Before have ah?
First year.
The electron move from the what?
First year the slide was 1, 2, 3.
Huh? This is slide 12. 12 should be bottom.
Go from the negative to the positive.
This one got things to say huh? Oh, sorry.
Move from what terminal to
Let me see ah.
The electron.
negative, positive.
Oh, positive to negative.
No, electrons will move from negative to positive. So that's electron flow. So the previous slide, the electrons will move from negative to positive. Eh? This one.
Move from the negative terminal to the
Negative first and then then the other, this one is negative.
Electric current. Okay, you all got it? Any questions? Yeah, I'm waiting. That's why I'm asking you for questions.
From the
Negative to positive. Who don't know what to fill in one? You all got it or not? Yes, Rian. Conventional current. It's okay. Science is like that one. There are many things. Why? Okay, is it okay? Don't drop science lah. Don't drop science. I'll be so sad. Spend 1 year with you on the drop science. I can't. I don't do anything. I want you all to do well.
When your birthday
My birthday, huh? August.
August what?
Don't tell you. August 9, National Day. Okay, are we ready?
August 9,
Okay. Eh? You're not my Facebook, right?
You got
Oh, I
Facebook?
think I saw before.
You got Facebook?
Irene Chan.
Somebody added.
Irene Chan.
Somebody added. Okay. Okay, next one. How? Follow me. How do we next slide is how do we measure an electric current? This one we talked before, right? We talked about it before, right? So it says the magnitude. Magnitude means size. You can put that bracket. If you don't understand the word magnitude means size. How big, right? So the magnitude of an electric current is measured with an ammeter, right? Ammeter. How to spell ammeter? A-M-M-E-T-E-R. Ammeter, right? Ammeter. And then the no, it's spelled correct. A-M-M-E-T-E-R. Ammeter. Oh, I didn't like sorry. Okay, then the SI unit is ampere. This one. Ampere. And the symbol is A. Okay, symbol is A. Can I? Oh. Yeah. Hey. Oh, okay. So for example, if let's say we want to measure, okay, let's take for example, we want to measure the current in this circuit. How to measure? Ruler? No. I know. Put you one side, put your ear, left ear, then possibly right ear, then you measure for me.
What are you talking about?
If you want to measure the current, how to measure?
Why is it then?
Use voltmeter.
Use current. Ammeter lah. Then put where? How to put? Put no piak like that.
Take out all you put.
So if you want to measure the current of this, that means you want to measure how much electrons are flowing. What you need to do is connect the ammeter here. Like that. Then this will tell you how much is flowing through. Okay, don't worry, we'll try this out in the lab. We'll try in the lab, don't worry, we'll try in the lab. Tomorrow. I don't know when when Mr. Cher is ready for us. Sure. Once we're ready, then we'll try it out in the lab. Okay, we'll play with some of the ammeter, voltmeter, and see how it works. You can play with me. Measure. Then they can put different bulbs. Okay, Ken? Questions? Okay or not? Today you all be more restless, huh? Why,
Last period.
Why so many things, huh?
Cause tomorrow by then.
Those that you
All remedial, huh?
Yeah, come on,
Those who need help.
So who needs help?
Then ah.
Ray.
Alright.
Alright. Okay, 1 o'clock. Okay. Okay or not? Still can carry on or cannot already? Huh? No, I just want to see you. Carry on. But I thought that nobody listen and no point. Okay, wait. I know. No, I'm not wasting time. Because even if I keep talking, nobody listen, also no point. Are you guys okay? Okay, right? People is like, people, I know not chapter 12 lah, but this one also must study lah. Okay. Yeah, those of you got sleeping card must wake up already. Those who no sleeping card also must wake up already. Cannot. Yeah, go and wash.
Good morning. You want breakfast?
Okay. Yeah, go.
Okay, help me.
Yeah, need to take a break or not? Oh, no need. Need lah.
什么也是可以。
5 minutes ah? No need. Need or no need? Okay. Sure ah? Okay. Huh? 2 minutes? 1 minute? Don't want? Okay. 1 minute walk around. Can? Don't want? Okay. Alright. Okay, next slide. It says, so first of all, right, you must understand that an ammeter is connected in series. Okay, now we're going to study a little bit about what is series and parallel. Okay, series. Series, okay, listen. Series is like this. That means in series. That's quite stupid, right?
What do you mean?
Series means like that. If you follow the flow of the current, that means the current does not branch out. It follows in sequence. Like for example, this. I can't until you are ready. Now,
Why do you have a speaker here?
this circuit is in series. If you follow, the flow of the current or the flow of the electrons, you realize that all the different, these are called electric components. They are one after the other. That's series. So like, for example, if you follow the clockwise flow of the electron, it goes to the ammeter first, followed by the bulb, and then followed by another bulb before coming back. So, one after the other. So, series equals one after another. This is the simple understanding of series. So, an ammeter must be connected in series, one after another. Now, what is parallel? Yes. Parallel means you have branching out. For example, this is parallel. This is series. Okay? That depends. You can try it when the experiment comes. But that's a very good question. I mean, a very good question is, what's the difference between connecting in series and connecting in parallel? Very good. So, what Ben said is very important because in series is one after the other. Parallel means branches. Okay, that means it's branches out,
So
right?
it's like that, right? The diagram. It's over parallel.
This is parallel.
Oh, this one.
This is
Then
series.
what?
Yes. Yeah, correct. So the idea of what Ben said just now is, if in series, one light bulb is to blow. For example, light bulb spoiled already.
The rest cannot go.
This light bulb
Or
will also not light up because there is a gap
Yeah, but if what is the battery?
in the circuit. There's an incomplete circuit, there's a gap. Therefore, this will also not light up.
But the battery rest.
But it's strong. No matter how strong, unless you tell me 1000 volts, then
Why
you
not?
jump across. But if there's a bulb that can tahan 1000 volts, you find for me. Okay. But in this case, in parallel, if one bulb is broken,
The other bulb here.
the other bulb will still light up because the current can still flow this way. Okay?
Brighter ah.
Very good question. We will find that out when we do the lab, then you tell me.
Parallel is brighter.
Yes, correct. The circuit setting up of our houses, homes, is usually parallel. But saying that, but have you guys ever had electric short circuit in your home before? Have, right?
I was thinking.
There is a box. You know the circuit breaker? So when something happens to the electric system in your house, usually, let's say even if a bulb blow or your kettle spoil or something, like for example my house, my microwave got problem, every time I turn on the thing will trip, the circuit breaker will trip and then the whole house power will go off. Then you have to reset, right? Yeah. Okay, question, wait, before question first. Huh? Electric what? Eel. Oh, eel. I don't know. 1,000? 500? I don't know.
Here we got.
Electric eel. Vivo is asking about electric eel.
No?
Huh? Oh. I guess we'll see that.
You put in M1,
Okay. Questions so far? Okay, give you 1 second. Okay, now to fill in the blanks, okay, so an ammeter is connected in series. Then this one is important because in the lab you try to connect. Okay, so it says the positive terminal is connected to the positive side of the cell and vice versa. Now, when you take a look at the ammeter in the lab, it will look something like this. There's a box, then there's a needle like that one. Okay?
Yeah.
There's a box, something like that one. Sorry, Mr. Chan's drawing very lousy. Okay, now, you will notice that in the lab, right, there are 2 little plastic knots here, and one is colored red, one is colored black. Now, these 2 colors are very important in electric circuits. Very important in electric circuits, okay? As Benjamin has said, red stands for positive. Red stands for positive. Please write it down in your book somewhere. And black stands for negative. So what this slide is saying is, when you connect the ammeter, for example like this, you must connect this side to black. So black must be here, and you must connect this side to red. Right? Red is here. Very good. Don't worry, we'll try it out. Now, what happens if you connect the other way? It will work. No, you'll move.
current will not be
You
so
cannot control. Ah.
No. Okay.
There'll be no, there'll be no light.
No. You will still have light now. It's okay. Tell you what. Don't panic. We will try in the lab. And then you tell me what happened. Soon. As soon as Mr. Che has the stuff ready, we'll go. Okay? You still work?
It's a switch.
M meter. This one is different. This is different. This just tells you that you must connect the negative to the black and the positive to the red. That's all. This is not a battery. Okay, now, if some of you feel very confused and don't know where we are heading, it's okay. Stay calm. Stay calm because some of these things you need to play with it in order to know a bit better. It's okay. Okay? Now we're just filling up the theory first. Okay, any questions?
No.
Okay, next one. Now, the other concept we're looking at is called potential difference. Now, do you remember potential difference? We said what is potential difference?
How fast the electron?
How much energy? How much energy, right? So let's take a look. Yes, we will also. Very good. Okay, next one. Okay, take a look. The potential difference slide. Do you see the potential difference slide?
Yes.
There's a bottom left. Now, this is what it says. The potential difference between 2 points is a measure of the amount of potential energy. That's the first blank, right? Is the first blank?
Yeah.
Just write there potential energy. I'll write for you, just in case you cannot spell. Potential energy. Okay, potential energy. That is changed into other forms of energy when an electron passes between these 2 points. So the next blank is other forms. Other forms. Okay, yeah. Okay, okay, now. Can Okay lah, just a bit more. Next sentence. An electron leaving the negative terminal of an electric cell has higher potential energy. At other points in the circuit, its potential energy is lowered. Okay, so one way to look at it is that here is high.
Plus is low.
Here, low. Okay, can? High energy. Okay, can? No, yeah. Okay, come, let's try. Let's go. Now, one of the ways I try to understand this is to imagine that this circuit is like a slope. Okay? You know that the slope, when it's at this point, it has most potential energy. So imagine this is the positive side. Negative side. And this is the positive side. Okay? Now imagine every time it travels, when, for example, I change this a bit. Imagine the light bulb is a mini slope in this slope. Okay, I'll show you what I mean. Okay, I'm going to take out this one, one more bulb here. So 3 bulbs. Huh? Now, this is model. Model is just a way of understanding how it works. So I'm giving you a model. Now, imagine this is the negative side. The electrons travel. When they travel, no change in energy. But once it hits the bulb, this is bulb 1. Once it reaches bulb 1, the potential energy is like slide down. Why? Because some of the electrical energy is used to power the first bulb, to give out heat and light. Right? Heat and light. So basically what happens is some of the energy of the electrons give up already, lose some. Because it's used to power the bulb. So you can imagine the electrons travel like that. Once you reach here, right, reach the bulb, right? Once it passes through the bulb, they lose some energy. Then they travel some more to bulb 2. Then lose some more. So lose some more. Then they travel to bulb 3. Again, lose some more. Okay? So potential difference, the concept is something like this. As it travels from bulb to bulb, they will lose more and more energy until it comes back to the positive terminal or positive end of the battery. Question? No, I'm going to ask you a question. Now, if I say all the 3 bulbs are the same wire, same everything, what do you think will be the slope look like for the 3?
Same voltage, frequency is the same.
Correct. So the concept you must have is, if the 3 bulbs are the same, the amount of potential energy lost by each bulb should be the same. At the moment, no need. But I'm just telling you, it should be the same. So therefore, the brightness of the bulb should be the same. And the slope should be the same. Now, if for this one that I draw, does it look like the same or different?
Same.
Different.
Correct. The last one is a bit different. So therefore, the last one is a different bulb in the way I draw it. Okay, Benjamin. Slowly, parallel a bit different, but I want to do the series one first. Do you understand this analogy?
Yeah.
Does it help to understand how it works? Is it better? Okay, some yes, some no, so it's okay. Okay, questions? Do you have questions?
No?
No, okay,
There was a series one.
Huh?
Isn't it series?
Series one.
No, I mean for
Parallel later lah.
Sure, but usually not like the first bulb brighter than the last bulb.
Good point also, but don't worry. This is like we call it a thought experiment now, thinking. So when we do the experiment, then you tell me what happens if you connect more bulbs. Then what happens? Okay, you can think about it. Okay. Any questions so far? Did we fill in all the blanks? Haven't, huh? So the second sentence is this, and I didn't say, huh? Okay, let's try, an electron leaving the negative terminal of an electric cell has a higher potential energy, and at other points the potential energy is lower. Okay, simple. Next slide. How do we measure potential difference? SI unit is, what's it called? Volt. And the symbol is V. Okay? Volt and V. And then to measure is a voltmeter. Okay. Check. Yeah, I also like zombie. Okay? Can or not? As higher. Okay. Shall we start? Or you had enough? Or you want some more? Still can ah?
I want for a C.
Ah, like that. Yeah, give up already. See people give up already.
You want a
And Nathaniel has given up, don't
So it's
know,
okay.
30 minutes ago.
They don't want
Hungry ah? Okay, hang in there, hang in there. Okay, what is the next slide ah? Oh, resistor already lah. Okay.
No, voltmeter.
Ah, voltmeter ah? Hey, I thought I tell you voltmeter already.
Then got two more.
Oh, okay, let's finish up the voltmeter. Okay, now. Okay, just finish up the voltmeter, okay, then we'll take a break. Yeah, I know, we finish up. Okay, now. Voltmeter is connected in parallel. Okay, so for example, if I want to measure the voltage, that means the difference of this bulb, okay, of this bulb, for example, what I need to do is,
move it.
I need to connect a voltmeter like this.
What a meter.
No, I thought it's connected to the bulb.
Jack, cannot just put in between and
Cannot.
bulb.
Cannot.
No, I thought it's connected to the bulb.
You must be, voltmeters must be connected across something. Okay, now, if you, okay, wait. If you put a voltmeter like this,
Cannot. So that voltmeter only measure.
if you put a voltmeter like this, the reading will be 0 because there is no difference between this point and this point. Think of voltmeter as measuring the steepness of the slope. So if I say I want to measure the steepness of the slope between this point and this point,
Where's my
no steepness. I mean no gradient. But if I want to measure the steepness, I must measure when there is a drop, correct? There must be a drop. From the beginning point to the next point must have a drop. Then I can measure the gradient. Hang on. Yeah, you're right. That's the math gradient. So therefore, voltmeter must be connected between, like that, the light bulb. This is called parallel. This is the second bulb. Sorry. When?
Can you connect to the bulb?
No. So if let's say the bulb like that, right? The bulb is like that, right? Let me draw a bulb. The bulb like that, right? Then when you connect the bulb, it is one wire to the bottom, one wire to the side, correct? So if you want to connect the voltmeter, you connect the wire here and here. There. In metals also, the red and the black. Voltmeter also got red and black. So the red must connect to the positive, the black must connect to the negative. But the bulb itself got no difference, right? You connect the positive or negative here, still the same, will still light up. Oh?
So, got the voltmeter take the energy.
Very good question. We will try it out in the lab. Very good question, Benjamin, excellent. Okay. Can? Can not? Okay not? Okay ah? Hot, I know lah, also very hot lah. Dying already ah? Okay. Anything later?
Two more.
Voltmeter is connected.
Okay, maybe we finish up with the electrical appliance one. Then we're done. Okay, it's okay? Just the last slide. Okay, last slide. Then we take a break. Hey! Parallel. Yeah.
Very funny, you know.
The positive terminal is connected to the red Good. So last slide. In electrical appliances, electrical cells are connected in series. And then after that, when you connect in series, the voltage increases. So the total voltage is the sum of all the voltage of the individual cells. That's it. Finish. Okay. Now, what is resistance? Now, basically, the idea that you want to get away with is that if you take a look at the blanks, right? It says, if you take a look at the bottom left, right, where at the bottom left slide, it says what is resistance. The main idea is that resistance is in a circuit acts as an obstacle. Okay, the word is obstacle. Obstacle against the flow of electrons. That means preventing the electric current from flowing. What's the obstacle? Oops. Okay, preventing the flow of electrons. So the components are said to have resistance. Okay, that's the word, resistance. Next blank. Now, for your information, every electrical component in an electric circuit has resistance. Every component. So, what are the common components that we have introduced to you? The light bulb, the bulb, example. What's that? Bulb. Okay, example, the bulb, or lamp. What else? Even the switch to some certain extent, but we don't write that there. The cell is the source. The battery is the source, so it doesn't have resistance. Of course, resistors. Here's the very interesting thing. The ammeter and voltmeter, they are components that we introduced, but the resistance on these two things.
They don't have much resistance.
Hang on. Yeah, yes and no. You are right for some cases and wrong in some cases. Now, do you remember for the ammeter, how is it connected in the circuit? Ammeter, do you recall? Okay, ammeter measure what first? Wait. Ammeter measure what?
The amount of electricity.
Amount of electricity flowing through, right? And what is it called? Ampere, yes. And what's the unit? A, right? It's A. Now, how is it connected? Yes, the positive is connected to the red color on the ammeter. The negative is connected to the black color on the ammeter. But with respect to the circuit, how is it placed in the circuit? Sideways. Series. Very good. Now, the component for the ammeter, because it's supposed to be placed in series, interestingly, the resistance here is supposed to be close to 0. These are notes. No, these are notes. I want you to add in certain things. These are extra information I want you to have. No, haven't. So the two blanks is optical and resistance. These are extra things I want you to write in. Now the voltmeter, remember the voltmeter measures what? Voltage, right? And how is it connected with respect to the circuit? It's in parallel. Now the voltmeter is understood to have very high resistance. Voltmeter lah.
It can be a parallel and a series together.
Can, but let's not go there first lah, slowly. But it can be done, yes, of course. Okay, can Okay, now the next blank the greater the resistance in the circuit, the lower the current. Okay, so you write that down in the blanks. The greater the resistance, the lower the current. Meaning when the resistance is very high, very little current pass through it. Now, here's the question. If the voltmeter has very, very high resistance. No, voltmeter. Remember the voltmeter is like that? Remember, I draw a circuit like that, right? Oops. I draw a circuit like that, right? Then I connect it to say one bulb here, right? Then if I want to find out the voltage across this bulb, I connect a voltmeter like that, correct?
Yes.
Now, here's the idea. Now we know that the bulb and the bulbs have resistance. That is why, right, you have lesser and lesser current flowing through it. But the voltmeter is supposed to have a lot of resistance. Meaning what? The note say, right, the higher the resistance, the lesser the current. So therefore, very little current pass through here. Very correct. Okay? Very little current. Very correct. Yeah, right. Kind of. The ammeter of the put. The ammeter must put here. Like that. Must put in series. You can put here, put anywhere, and you'll have the same reading. You'll find out when we do the experiment.
Is that the voltmeter?
Put here.
Yeah.
Cannot. Ammeter measures current, yes. Measures voltage.
Put the ammeter on the other side, right? The reading will be lower.
No, it should be the same.
The other side.
No matter which side you put. But we can try in the experiment, you see how it goes. Brian? The last blank is SI unit for resistance. Ohm. Oh. And the symbol is, remember the symbol I drew for you before? Ohm. That's the symbol. Alright. Okay so far? Okay, this symbol is the Greek letter called omega. Omega. Yeah, it's the very. I told you right, James Bond watch, I said before. Yeah, I see.
The James Bond and Mr. Bean.
Okay, never mind.
Lesser or lower?
Greater or higher? The lesser the color. Okay, Ken? Okay, next slide. So what are resistors? Very quickly, right? Resistors, the first blank is this, right? Electric current such that will operate properly only if the correct amount of current flows in the circuit. The answer is correct. Correct amount. You know what? Is it okay if I put it on the screen? I think it's easier for you to see, right?
Yes.
I think see faster lah.
Yes.
Then you can draw the dog.
Can somebody help me with the projector? Switch off the light. Switch off. Can you please switch it on to me? Right. Hey, where's the? Can somebody help me drop the? Which one can this one ah? Thank you. Alright, does it work? Your umbrella looks very 迟钝。Okay, thank you. Okay. Alright, let's see if it's better. Very dark, huh? Okay, Ken? Okay, so just look and then copy and then I'll explain at the same time.
Thank you.
Thanks, guys. Just don't fall asleep, right? See people fall asleep, right? Okay, good. I'll buy you more. Jet stream, right? You know, Acro ball, fire. I prefer use jet stream. Okay. Okay. Alamak, see half an hour left. Yeah. This is the bottom right slide. Okay, so the idea is this, right? Electric circuits and equipment will operate correct amount, only the correct amount of current flows. To control the amount of current, we use resistors. Sorry. Okay, they are real starts, yeah. It's another word for variable resistor. Yeah, but you tell me variable resistor is fine. Okay? All got it? Can, huh? Okay, next. Real start. You don't need to know that word, but at least you must know variable resistor. Okay? Okay, so basically, right, fixed resistor has fixed resistance, of course. Fixed. And then can range from a fraction of an ohm to thousands of ohms. Okay? So this is I know it's very small, but this is a symbol for fixed resistance, which I told you before already. It's just one rectangular box. Variable has an arrow. Yeah. Across it. Yeah, diagonally across. That's it. Very simple. Okay? Not difficult. They're all in your book. Again? Alright, next. Wait. Okay. You all must write faster. Focus. That's the symbol of resistance. It's a rectangular block box. No need lah. That is the symbol. Yeah, that is the symbol. Okay, next. Okay, so variable resistor is that the resistance can change. Okay? And this is the symbol. It's in your slide. Self-control. Don't stroke here, stroke there. Self-control. Okay, so variable resistance. And the idea is that, okay, here's the idea that you must, this is a very important idea. Please highlight this idea. When the resistance increases, the current decreases. When the resistance decreases, the current increases. Important concept. Yeah, opposite lah. So, greater resistance, higher resistance means less current flow. Okay, lower resistance means more current flow. Now, very simple concept is this. Do you guys have, at home, do you guys have those rubber tubing connected to your hose, to your tap? The hose. You have, right? I wash car, or sometimes I have one, so I wash my toilet floor. Do you have that? Now, listen. Those of you who have, you will notice that if you decrease the circumference of the hose, that means you pinch it or you squeeze it, right? More or less water come out. So the idea, okay, wait. You all must remember this idea because it's similar to the concept of electricity. So remember this, Now, at home when you switch on the tap, right, it says connected to the rubber hose. If you squeeze the rubber hose to a smaller circumference, less water will come out. Hang on. Less water will come out, right? But if you return it to its normal size, more water will come out. So the idea is when you increase resistance by reducing the circumference, the less current will come out, less water will come out. But you guys are correct to say that the pressure goes up. The water can go further because of increased resistance, and therefore the corresponding concept the corresponding concept is the which is the other measurement of electricity? We have current, voltage, very good. So if voltage is a measurement of energy, so the idea is if the current is very, very small, then the voltage becomes high. Same as the water pipe, same concept. So therefore, I want you to write it down. Write it down in your notes. Greater resistance. No, it's there, right? It says that greater resistance there. This one. When the resistance increases, that means greater resistance, the current decreases. Can you write there? Put there, put a caret, put an arrow there. Voltage. Find space. Voltage what? Voltage increases, yes. Then, when the resistance decreases, the current increases, voltage decrease, yes. Same as your water pipe. Water pipe, you turn on the tap, you squeeze the pipe, more or less water come out. Less water come out, but the pressure higher, same. I repeat, when the resistance increases, the current decreases, voltage increases. Right? When the resistance decreases, the current increases, voltage decreases. Just remember the water pipe analogy. More energy. Same concept. Okay, I hope you will remember the water pipe analogy because that's something that helps me to understand current, voltage and resistance. Okay, questions? Can I? All right. Okay, let's go on. Okay, so what is the use for variable resistor? I told you guys before, like for example, if you have thermostat at home, like changing the aircon temperature, or sometimes when you help your mother iron clothes. Do you iron clothes? You all used to have to turn the dial, right? Like sometimes you need a hotter temperature, sometimes you use cooler temperature, right? If you iron very delicate material like silk and everything, you don't use very high heat, you'll melt. Like your pants. If not, right, for example, the dry fit material, if you use very high heat, right, you'll melt. Yeah, go on hold it, you'll burn, yes. Alright? Good. The fan, the knob, right? Like the fan, you can adjust. Then this one also, right? Good. Very good example. This one. This is a rheostat. This one. Because you can change the speed of the fan. Very good. Excellent. Okay. I wish you have rheostat. I wish I can change your volume. Okay, ready? Okay, next one. Rheostat is more generic. Thermostat is to control. Yes, exactly. Okay. Ken. Zen, are you okay? Not okay. Sick. Don't go sick bay. The one. Okay. Zen. Okay, continue. Alright. Now, and I talked to you about this before, right? So all you need to just fill in the blanks. Series, parallel. So right here, series, right here, parallel. Very easy on this one. This one I've done already.
How come the battery is series, not parallel?
We can talk about that also. Malcolm asked the question, can the batteries be connected in series and parallel? Yes. Okay, so very quickly, just a simple question, not simple, but just a question for you. Now, if each cell, hang on. Let's say each cell represents one battery, 1.5 volt. Now my question, I asked you this before, right? If you connect the battery like that, how many volts? 3, right? Now what if I connect in parallel?
6.
What if I connect the battery like this? That's a very good question. So let's consider. So if I connect the battery like that is series, right? And the total volt is 1.5 plus 1.5. Correct? So it's equal to 3 volts. But what if I connect the cell like this?
If it's still 1.5,
It's still 1.5.
And I connect a light bulb like that. So what is the voltage? Very good. The voltage should be still 1.5.
Why?
But, so what has changed?
duration of the battery life.
Just that you wake up battery.
You waste more battery. Okay, we shall try this out. Now, what happens is, I told Mr. Cher, I said, in the experiment that we're going to do in the lab next week, we will give you some standard experiments to try out. But then there will be one section that I will allow you guys to come up with any modification you want to, I don't use the word play, play means like not learning, right? But I want you guys to come up with any combination you want to learn about the circuit. And you can propose any combination you want. But you must draw it first and then you show me. Okay, now my idea is this, because I believe that you can learn while having fun. And I know that when I taught in my previous school, right, when I let my NT students play with components such as battery, bulbs, and everything, they will go crazy, try all sorts of things, and their main purpose is very simple one. They only have one objective. No, not enjoy. No. Yeah, to burst my light bulbs. See how many light bulbs they can blow at one time. So they connect like 10 batteries and they say, hey, Mr. Chan, you see I can burst this light bulb with 10 batteries. Then they pop, every light bulb they can explode. So then I tell them what's the point, right? I mean, I give you half battery already. Yeah. So now listen. I know that you guys would enjoy, at least most of you enjoy, like playing with the components that I give you. And I think it's okay. I think there's fun in doing that. But I want you guys to have an objective in doing it. So therefore, I'm going to allow you guys to plan your circuit. And then you tell me what you expect to see. And then you try it out. Is that okay? I think that'll be fun. Right? I think that'll be fun.
Can the battery cell equally distribute themselves in the house?
It's a good question. I don't know.
Like, for example, the first speaker, right? They have three.
Guys, can you guys hang on? Clement is trying to say something. Thanks. Yes, Clement.
3 volts altogether, right? Can one light bulb have 1 volt?
Okay, very good question. So, listen. Here's what Malcolm is asking, and it's a very good question. Oh, sorry, Clement is asking, right? He said this. He said that this battery, right? This battery provides 3 volts. So if the lamps are the same, does it mean that the voltage across this lamp is 1 volt, 1 volt, 1 volt? So that was his question. My statement, my comment is, we'll find out when we do the experiment. There is, but I don't want to tell you what the formula is. I want you guys to take a look at it. Okay, no problem. I think it's a very valid question, Clement. Okay, come, let's continue. Okay, so basically the definition of a series circuit is each component is joined one after the other. It's blur, huh? Maybe it's a bit blur lah. Is it because it's not focused? It's running. No, this slide. Is it? Okay, can I borrow your chair? Shift the table. Is it better?
It's the same.
I think that's the best I can do. Okay. Thanks, Ren. Okay. This okay? So if it's in series, right? You guys got it? Have you got it? Written it down? If it's in series, so it'll be one after the other. And here's the important. Can you underline the second? Can you underline the second statement? The current that flows through each of the components is the same. Very important point. Can you underline? Highlight the second statement. Yeah. Highlight the second statement in your slide. Second statement. Yeah. The current. Hello. This one important. Second statement. You all got it? Do you understand what that means? Yeah. So, interestingly, right, when you connect a circuit in series, imagine that the electrons are like water, the wire is like a pipe, water pipe. The amount of water that goes through all the bulbs, or in a sense, all the components, is the same. Yes and no. We can talk about that another time. Because every molecule has a certain. In the balloon? Or static? Okay, that's different. Static. Okay, questions? You guys okay with this? Important, huh? So therefore the idea is that one bulb is removed or broken, no current flows, and the other bulbs do not light up. We know that. Okay, we can try that out on the day itself. Okay, next one. Okay, parallel circuit, right? Parallel circuit divides. Okay. Yeah. Okay, so in a parallel circuit, right, it actually divides or branches, and you realize that the second line is really important. The current from the battery divides and flows through each branch. Okay? So series circuit, the current is all the same. Parallel circuit, the current is different. Different branches are different. Let me ask you this question. Now there are, let's say for example, you take a look at this circuit, there are 3 light bulbs, correct? Let's say this is light bulb A, light bulb B, light bulb C. Now, if I tell you light bulb A has the highest resistance, followed by light bulb B and light bulb C, how much current flows through A compared to B compared to C? Okay, light bulb A has the highest resistance. Let's say we just give a number. Let's say light bulb A 10 ohms. 10 ohms. Light bulb B 5 ohms. Light bulb C 1 ohm. Let's say. Now I ask you, of the 3 light bulbs, because we know that the current flows through all 3 branches, which light bulb has the most current flowing through?
The one all the same. All the same.
So either you choose, so some of you say all the same.
Same.
Okay? That means the current flowing through A, which is 10 ohms, is the same as the current flowing through B, which is 5 ohms, the same as the current flowing through C, which is 1 ohm. Okay, some of you say that. How many of you say that? Okay. How many of you say that the current flowing through is different? That means the current flowing through A, B, C bulbs are different in this setup. Okay, different. Now, those of you who say different, which one is bigger? Which current is bigger?
Last one.
Is A the biggest or C the biggest?
C.
How many say C biggest? Okay, why C biggest?
Lower the higher.
Very good. So the correct answer is
C. Current.
because the bulbs of different resistance, we know that lowest resistance have highest current. Remember the previous slide? Remember not? Previous slide is lower resistance have higher current, highest resistance have lowest current. So therefore, they have different currents and C as the greatest. Okay? Can? Alright. Okay. Hey, do we have to calculate this? Wow, this one very hard to explain.
Let's go.
Just right first. I think this one you have to try. I'm so sorry. Sorry. I think our dear projector is not high definition. So much. Okay. 很多嘞，惨了这个。Hey. No. Why are your girlfriend there? Old girls are.
Your wife will be in danger.
Why?
Your wife might be in danger.
Why would she
Because
be?
maybe she's like, they never know.
Okay. Are we done? Are we done? Okay. Alright. Sorry. I want to try to understand this before I explain to you. Go. Okay, guys. Can I try to explain this? It's also quite confusing for me. Okay, listen. Are you ready? What are you looking at? Huh? What? Dreamcatcher? Okay. Very tiring. Okay, can I try to explain this to you guys? Cannot. Okay, now listen. I try lah. Okay, now the idea is this, what makes a bulb brighter or dimmer? Okay, now listen. What makes, because we know that resistance, current, and voltage are all related. Correct? Remember the pipe, the water hose analogy? If the hose has greater resistance, the water coming out will be lesser, but the energy coming out will be more. higher pressure. So same thing, if the resistance is higher, the current is lower. Current is amount. Resistance higher, current is
Lower.
okay, current is lower. Current is amount of water, right? So analogy lah. Yeah. Then of course the voltage will be higher. So higher resistance, lower current, higher voltage. Okay? Now listen. What affects the brightness of the bulb is actually the amount of current. I repeat, what affects the brightness of the bulb is the amount of current. So the more current that flows through the bulb, the brighter the bulb. Okay, can you write that down? Yeah. So current increases, bulb brighter. Can you write it as a statement here? Current increase, bulb brighter.
So voltage increase.
Wait, slowly. So can you write this down first?
Voltage increase. Current.
Okay? Is this okay? Hello?
Oh, okay, that one is
Bear with me lah. I know you guys are very bored. I'm trying very hard. Yeah. It's very calm. Okay, listen. Hello? Okay. So, now, frankly, right, if you ask me, I don't know how to make it easier for you all to remember a lot of things. So I try to use analogy, but if analogy doesn't work, right, it may mean that I have to just physically make you memorize certain things. No choice then. Okay. Now, do you guys, I know not every, okay, do you guys like to watch Chinese martial art movies? Now listen. Now, as with any good martial arts master, you know that every time you practice martial art, you have something called a mantra. Mantra, whatever. Now, what does it do? Now listen. Now what the mantra helps you to do is actually helps you to remember and focus on certain aspects of the martial art. I don't know whether Wushu is still the same, but if you... Okay, at least I know you are interested in Chinese martial art. Okay, now listen. Now, I know I'm not teaching Chinese martial art, but what I would like to do is, hopefully, right, if I can reduce some of the concepts or electricity into mantras for you to memorize, it will help you understand the topic better. Is it okay?
Yes.
Can or not? Now, so far, right, our concepts revolve around three things. What are the three things? Resistance, voltage, current. Yes. Okay, now listen. Before we go, listen. Everything that we learn about electricity has to revolve around these three things: resistance, voltage, current. Okay? Is it okay? Now, for all of these three concepts, you must always remember SI unit, what it measures, and how does it affect one another. Okay? So, bottom line today is this. This is your mantra for today. I know. Now, if you are the sort who cannot memorize, this will be, you write down, but this will be the same analogy as the water pipe one. You can take a photo, but it will be the same as your water pipe one. Remember the water pipe? Resistance, you squeeze, less water come out, but high pressure. Right? If the water hose you don't squeeze, the more water come out, but less pressure. Okay? Then, thank you class. Thank you class.
Thank you.